the universe will end. That's not a guess, it's not a prediction, it's a guarantee written into the fundamental laws of physics. Every star you see, every galaxy, every thought you have is part of a cosmic story that has a final page. The real question, the one that should keep you up at night, isn't if it ends, but how? Will it be a slow, silent, and infinitely lonely freeze, where the last star fades to black, leaving an eternal tomb of cold and darkness? Or will it be a sudden, violent, cosmic rip, a finale where the very fabric of space turns against itself and tears even atoms apart? Or could it be something stranger? A sudden glitch in the operating system of reality that erases everything we know in the blink of an eye, without any warning at all? Tonight, we are not just stargazing. We are running the final audit. We're opening the universe's books, examining every entry, and we're going to find out what happens on the very last page. Let's get started. Before we can seriously audit Doomsday, we need to get two absolutely critical concepts straight in our heads. These two forces are the titanic engines driving the fate of everything. Get these, and the rest falls into place. First, let's talk about entropy. Now, you've probably heard it called disorder or chaos, but that's not quite right. A better way to think about it is this: entropy is the unstoppable march from a special state to a generic one. Imagine building a magnificent sandcastle on the beach. It's a highly ordered, specific structure. That's a low entropy state. Now, what happens over time? The wind, the waves, the tide, they break it down. The sand spreads out across the beach. The sand is still there, but it's no longer in that special, ordered sandcastle shape. It's in a generic, high entropy state. The second law of thermodynamics, one of the most unbreakable laws in all of physics, says that the total entropy of a closed system, like our universe, can only increase. That's it. It's a one-way street. Your coffee gets cold. Your ice melts. Buildings crumble. Stars burn out. This law is the arrow of time. The only reason you remember the past and not the future is because entropy was lower yesterday than it is today. Entropy is the universe constantly cashing in its specialness for genericness. It's the universe's unstoppable march towards becoming lukewarm. And when everything is lukewarm, nothing interesting can happen. Okay, concept 2, dark energy. If entropy is the slow, inevitable decay from within, dark energy is the bizarre, mysterious force pushing from without. Back in the 1990s, astronomers were looking at distant supernovae to measure how fast the universe's expansion was slowing down. They expected gravity to be putting on the brakes. But they found the exact opposite. The expansion isn't slowing down. It's accelerating. Something is pushing space apart, faster and faster over time. The best analogy is baking raisin bread. As the dough rises, all the raisins move away from each other. But with dark energy, it's like the yeast is getting stronger over time, making the dough rise at an ever-increasing rate. We call this force dark energy because we have absolutely no clue what it is. It seems to be a property of space itself. For every new cubic meter of space that's created, a little bit more of this repulsive energy appears. It is a tiny, tiny amount of energy in any given spot, less than the energy of a single atom in a whole room. But the universe is big. Unimaginably big. And over cosmic distances, this tiny push adds up until it is the single most dominant force in the cosmos, overwhelming the gravity of every star and galaxy combined. Right now, it's behaving predictably, like a fixed cosmological constant. But if that constant were to change, even slightly, if that cosmic yeast were to suddenly get weaker or terrifyingly, much stronger, the consequences would be catastrophic. Alright, you got it? Entropy is the universe running out of useful energy. Dark energy is space itself pushing everything apart. With those two concepts in our toolkit, we can run the first, and most likely, scenario for the end of time. This is the fate our universe is currently headed for, based on every piece of data we have. Welcome to the heat death. The big freeze. In this future, dark energy keeps its cool. The cosmological constant stays constant, and the universe just keeps expanding. Forever. For the next 100 billion years, things will still look somewhat familiar. But the relentless expansion will be pushing galaxies apart so fast that, one by one, they will cross a cosmic horizon. Their light will no longer be able to reach us, no matter how long we wait. They will blink out of our sky, forever. The night sky of our distant descendants will be a lonely, dark place, containing only the stars of our own Andromeda galaxy, after the Milky Way and Andromeda have merged. All other galaxies will be gone. Then, the slow decay really sets in. This is the beginning of the degenerate era. Around 100 trillion years from now, the clouds of gas and dust needed to form new stars will be too thin and spread out. The last new star will flicker to life and eventually die. The universe will stop making new light. The stars we see today, Like our sun, will have long since burned out, leaving behind a cosmic graveyard of cold, dead remnants. White dwarfs, the collapsed cores of sun-like stars, will cool and fade for trillions of years until they become black dwarfs, frigid, inert chunks of crystallized carbon and oxygen, essentially universe-sized diamonds floating in the dark. More massive stars will have left behind neutron stars, city-sized objects so dense a teaspoon of them would outweigh Mount Everest. And of course, the black holes. This is where it gets really weird. What happens to all that dead matter? Here's a wild card: proton decay. Our best theories of physics, called grand unified theories, suggest that protons, the bedrock of every atom, aren't actually stable. They have a half-life, just an absurdly long one. We're talking 10 to the power of 36 years, or even longer. If this is true, then over these unimaginable timescales, all matter as we know it will simply dissolve. Those black dwarf diamonds, the neutron stars, all of it. They will slowly disintegrate into a mist of low-energy particles and radiation. The universe will become even emptier. But what if protons don't decay? Then all that matter will remain, and the universe moves into its next, even longer phase, the black hole era. From 10 to the power of 40 years onwards, the only major players left in the universe are black holes. They will be the last remaining organized structures, silent gravitational monuments to a bygone era of stars and galaxies. But even they are not eternal. Thanks to Stephen Hawking, we know black holes are not truly black. They leak. At the edge of a black hole's event horizon, the quantum world gets chaotic. Pairs of virtual particles are constantly popping into and out of existence. Every now and then, one particle falls into the black hole, and its partner escapes. Because of the weird accounting of cosmic energy, this escaping particle carries away a tiny, tiny speck of the black hole's mass. We call it Hawking radiation. It's an incredibly slow process. A black hole the mass of our sun would take 10 to the power of 67 years to evaporate. The supermassive black holes at the centers of galaxies? They could last for 10 to the power of 100 years. A number so large that if every atom in the observable universe were its own universe, with its own lifetime, that still wouldn't come close. But that clock will eventually tick to zero. And as the very last, most massive black hole shrinks, its evaporation rate will skyrocket. In its final moments, it will release a flash of high-energy gamma rays, the final firework in an otherwise completely dark and silent cosmos. And after that last whisper of light, it's over. We enter the dark era. The universe becomes a thin, cold, uniform soup of stray photons, neutrinos, and maybe some electrons and positrons, all drifting infinitely far apart from each other. Entropy will have finally, totally won. The universe reaches a state of maximum entropy, a final thermal equilibrium. There's no difference between hot and cold, no gradients left to power a star, a thought, or a choice. Nothing happens. And nothing will ever happen again. Program halted. That's the slow fade. The long goodbye. But what if the universe doesn't go out with a whimper? What if it doesn't fade, but gets deleted? This brings us to scenario 2, vacuum decay. And I'm going to be honest with you, this is the one that is the most existentially terrifying. It is a glitch in the very matrix of reality. See, that empty space all around you isn't truly empty. It is soaked in invisible quantum fields. The most famous of these is the Higgs field. You can think of it like a field of snow covering the entire universe. As particles move through this snow, they gain mass. A photon has no mass, so it's like a ski, zipping over the top. A massive top quark is like wearing snowshoes. It sinks in deep and is very heavy. Now, the energy level of that Higgs field, the depth of that snow, is what determines the rules of physics. It's our universe's vacuum energy state. We assume that we're at the lowest possible energy state, like being in the deepest valley in the entire landscape. But what if we're not? What if we are just in a shallow valley, and right over the next hill, there's a much deeper, much more stable valley? This would make our vacuum a false vacuum, a metastable state. Our entire universe, everything we know, would be living in a penthouse apartment, built on a cosmic trapdoor. And all it would take is one tiny quantum event, a random quantum fluctuation, like a ball that doesn't have the energy to roll over the hill but suddenly just tunnels through to the other side, somewhere, anywhere, in the cosmos. And that trap door would spring open. A bubble of the true vacuum, the more stable reality, would appear. This bubble would detonate outwards in all directions at nearly the speed of light. What would happen inside that bubble? We have no idea, but it wouldn't be good. The properties of the Higgs field would be different. This would change the masses of fundamental particles like electrons and quarks. The laws of chemistry would break down. Atomic nuclei might become unstable. The very structures that make us, the Earth, and the stars possible would be instantly invalidated. You, me, and the Andromeda Galaxy would be erased from existence not by fire or ice, but by having the rules that permit our existence fundamentally rewritten. You would never see it coming. It's the ultimate light switch off. One moment, our universe exists. The next, it's replaced. Now, before you start having a panic attack, I have to tell you what our best physicists think. By precisely measuring the masses of the Higgs boson and the top quark at the Large Hadron Collider, they can calculate the stability of our vacuum. The current consensus is, we're probably okay. The calculated lifetime of our false vacuum is stupendously long, maybe 10 to the power of 130 years or more. Far, far longer than the age of the universe. But the keyword there is probably. These calculations are at the edge of our knowledge, and if there's new physics we haven't discovered yet, all bets are off. The probability isn't zero. The trapdoor is real. So we have the slow freeze and the instant glitch. But there's a third option on the ledger. One that isn't cold and silent, but violent, chaotic, and loud. Welcome to the third scenario, the Big Rip. This all goes back to dark energy. The Big Rip is what happens if dark energy is not a stable, constant force. What if it's something more sinister? Something physicists call phantom energy? This is a hypothetical form of dark energy whose density increases as the universe expands. It's a runaway feedback loop. More space creates more phantom energy, which pushes space to expand even faster, which creates even more phantom energy. It's like a cosmic balloon that gets harder and harder to blow up the more air you put in it, until the pressure inside becomes infinite, and the balloon doesn't just pop, it's torn to shreds. This runaway expansion would become an uncontrollably powerful, repulsive force, and it would systematically unbuild the entire universe. It would happen in a series of predictable and horrifying stages. And we can even put a timeline on it. Let's assume the Big Rip is scheduled to happen about 22 billion years from now. Here's the countdown to dissolution. About 60 million years before the end, the phantom energy would become strong enough to overcome the gravity holding the Milky Way together. Our galaxy would be torn apart, its stars flung into the rapidly expanding void. A few months before the final moment, the gravitational pull of our sun would no longer be enough. The solar system would be unbound. The Earth, along with all the other planets, would be cast off into darkness. About 30 minutes before the end, the Earth itself would explode. The phantom energy would overwhelm the gravitational and chemical bonds holding our planet together. In the last few fractions of a second, the terror would reach its ultimate crescendo. With picoseconds to go, the electromagnetic force would fail, and atoms would be destroyed, their electrons ripped away from their nuclei. Then, in the last 10 to the minus 19 seconds, the strong nuclear force, the most powerful force in nature, would be overwhelmed. Atomic nuclei themselves would be ripped apart. The fabric of spacetime would, itself, be torn asunder as the scale factor of the universe goes to infinity. It is a true, finite end to time, and it isn't cold and silent. It is a tearing, screaming crescendo. So, there you have it. The freeze, the glitch, or the rip. A cold, endless fade, an instantaneous, shocking rewrite, or a violent, tearing destruction. So, how do we know which ledger is the right one? How do we audit our reality? This is where we have to step back and look at the deeper, weirder questions about our cosmos. Because the clues to the end are tangled up in the mystery of the beginning. We have to ask, why was the universe so orderly, so low entropy, at the Big Bang? Remember our sandcastle? The early universe was like a beach with every grain of sand packed into one single, unimaginably perfect grain. The odds of this happening by chance are, according to physicist Roger Penrose, so small that you couldn't even write the number down. Our entire existence is predicated on the universe starting in this highly unlikely, special state, giving it a massive reservoir of order to spend over the eons. The arrow of time itself is a consequence of this bizarre initial setup. But why? Was it a random fluke? Or is it a clue that our understanding is incomplete? And that dark energy number, that cosmological constant, it's the most embarrassing failure of prediction in the history of science. Our best theories of quantum physics predict that the energy of empty space should be 120 orders of magnitude. That's a 1 with 120 zeros after it, larger than what we actually observe. If it were that large, the universe would have ripped itself apart in the first fractions of a second. Instead, it's a delicate, persistent whisper, a value fine-tuned to an absurd degree to allow stars, galaxies, and us to exist. Is it really constant, or is it just changing so slowly that it's pushing us towards a big rip billions of years in the future, and our measurements aren't precise enough to see it yet? We simply don't know. And then there's the problem of information. According to physics, information can't be destroyed. When a black hole evaporates, does the story of every